Here's our next example. Let f be the vector field with components e to the xy, e to the xz, and x squared z. And let's start with a surface S, which is half of an ellipsoid. The ellipsoid is given by this equation right here. So this is a sort of a rotated ellipse, or a three-dimensional ellipse, if you will. In fact, by taking sections of this thing right here, you can see that the intersection of this ellipse with any one of the three axes, or any one of the three xz, yz, or xz planes, is just an ellipse. So for this, we want to take the half of the ellipsoid that lies to the right of the xz plane. So here's the xz plane right here. We want to take the whole ellipsoid, looks something like this. Sort of like a smooth, elongated football. And we just want to slice half of it across the xz plane and take the right half, which is what we get right here. So this thing is given an orientation. Whoops. It says oriented in the direction of the positive y-axis, while the tangent vectors are pointing in this direction. And what's the problem? The problem is this: we are tasked with finding the flux of the curl of f through this half ellipsoid surface. We'll find this flux by instead finding the line integral of f around the boundary of S. And that's easy enough to visualize. Remember, the surface S looked like this half of an ellipse right here. And so the boundary of S will be this circle that lies parallel to the xy plane. You can orient it like this. Again, remember, orientations have to match up. Our boundary curve has to be oriented in such a way that the orientation of C and the orientation of S agree according to the right-hand rule. So what is this boundary curve C? Well, here it is right here, but we need to find a parameterization for it. That's how we'll calculate the line integral. So we set about finding a parameterization for C. To do this, we begin by observing that C lies in the xz plane. So in other words, it lies where y is equal to 0. So we can obtain an equation for C, this one right here, by starting with the equation for the entire ellipse, which was what, 4x squared plus y squared plus 4z squared equals 4, and then taking y equals 0, that kills this term right here, which gets us this expression right here. So this is the equation for C in the xz plane. Of course, we can divide by 4 to get x squared plus z squared equals 1. And now we still need to find a parameterization. We need some function r, which is a function of a single parameter, which describes the curve z. Well, we've done this many, many times again. This is still just a parameterization in terms of sine and cosine of some parameter, because it's a circle. Here's what it looks like. Careful. X, so we want to parameterize this thing right here. X should be cosine theta and z should be sine theta. But remember, we're in the yz plane, so alert, y must be equal to 0. And that's what we see right here. So the parameterization is r equals cos theta, 0 sine theta. And this does indeed describe the circle which winds through the xz plane. Okay, we need, as we needed before, r prime, which is this right here, and then we need to evaluate f at the parameterization, which gives us this thing right here. Remember, we need the definition for the vector field f, which was what? E to the xz, e to the negative, or e to the xy, e to the negative xz, and, well, I forget, we have to look at it. So here's the original question. We rewrite as a line integral by virtue of Stokes' theorem, and then we parameterize to take us down to here. And then we fill in the blanks. We have found fr theta, that's this right here. We have found r prime theta, that's this up here. And after substituting those vector expressions, we go from here down to here. And then we take the dot product of these vector expressions and do some calculation. the dot product gives us this right here. Let me make a brief comment about this. So look, this integral is integral of negative sine theta plus integral of this stuff right here. I can write this as two separate integrals, right? Well, this first one is the integral of negative sine theta. But negative sine theta from 0 to 2 pi just looks like this. And if you integrate that from 0 to 2 pi, you just get 0. So this first integral from 0 to 2 pi of negative sine theta, is just 0. I used a little geometric argument here, but you could verify the same thing by calculating this. So this term goes away, it doesn't contribute. So we're only left with the integral of sine squared theta cosine squared theta. And I can obtain, or I can calculate that thing by writing each of these using the double angle identity. Sine squared theta is 1 minus cos 2 theta over 2. Cosine squared theta is 1 plus cos 2 theta over 2. At one time, you used this identity a lot, and you may have forgotten it, but I hope you at least remember seeing it and using it a few times. That's what we have to use to calculate integral of sine squared theta cosine squared theta to take us here. So, at any rate, we do that. Starting here and doing some calculation. Now it's just all a calc 2 integral. It's just a single variable integral. You just calculate this. You can do a u substitution. At the end of the day, you should do it for yourself. You just get pi over 4. So, the flux of the curl of this vector field through the half ellipsoid surface, through this half of the smoothed out football, is pi over 4, and we calculated that by calculating the line integral of the vector field around the boundary of the football, or the half football. So that concludes this example. I won't do any more examples at this point. If you really want to see another one, drop me a line, and I can perhaps find the time to do 1 or 2 more examples upon request. Thanks for your time.